In this lecture, we're going to continue developing our column generation technique. We're going to start introducing what we call the master problem. The master problem is pretty simple. The master problem is just the Danzig-Wolff reformulation of an integer program. Here we have pictured one of the reformulations. We're going to be interested in a lot of features of the master problem. This lecture is going to cover the features that we're going to need to develop our column generation approach. The first thing we're going to do is extract different columns of the master problem. In this case, a column is associated with a particular variable. Here we have pictured one of our columns. To find a column, we first fix our variable of interest. Our variables here are the lambda variables, lambda it. Note that lambda it is multiplied by a constant from our original integer program, and also the xit variable associated with the feasible solution that corresponds to this lambda. We take this c and this x, and we put it at the top of our column. This portion of the column corresponds to the objective function. The next part of our column corresponds to the link constraints. In this case, it's a superscript I times x. The third part of the column corresponds to the convexity constraints. In this case, this column of the vector is just the vector ei. The vector ei is a unit vector with exactly 1, 1 in the ith position. Whenever we write a column, we write, instead of xit, just the variable x. We do this because we know that implicitly there's going to be one column for every x variable. So we leave x free and look at all the columns over all x's inside of superscript xi. In addition to the columns, we're also going to be interested in the dual problem to the master problem. To introduce the dual problem, we need to introduce dual variables. In this case, we're going to introduce the dual variables pi and u. Pi is going to be the dual variables multiplying the link constraint. Pi isn't just a single dual variable, but in fact a dual vector. The dual values mu are going to multiply the convexity constraints. Again, this mu isn't a single quantity, but actually a vector. Our entire dual vector then is going to be the vector pi mu. These are the structures we're going to be interested in. We're going to be interested in the columns, one column associated with each feasible solution x, or alternatively, one variable lambda, and also the dual vector pi mu. The first thing we note is that because there's an enormous number of variables, there's an enormous number of columns. Our solution approach is going to effectively reduce the number of columns by focusing on just a subset. Before seeing how we're going to focus on a subset of columns, we're first going to simplify our lives a little bit. We're going to first simplify our lives by, instead of looking at an integer program, looking at a linear program. This linear program is going to have all the lambda it's fall within the range between 0 and 1, instead of taking values only 0 and 1. We'll expand to the integer case in a few lectures. The second way we're going to simplify our lives is notationally. Instead of writing all of the summations, we're going to fall back to our vector notation. In this case, we write our objective function as the dot product of c times lambda, write our link constraint as a times lambda is less than or equal to b, and write our convexity constraints as e times lambda is equal to 1. Keep in mind that this matrix E is a special matrix, although we don't really need to know the details, and that this vector 1 is actually a vector of 1s, and not just a single number. In this case, because we're looking at the linear program, we're going to let the lambdas be any positive number or any positive vector. Note that when we write all these quantities, such as c, and in particular a actually includes the terms associated with feasible solutions xit. Now with these simplifications and notation in hand, we can talk about how we're going to restrict our attention to just a subset of columns. We're going to call our original master program zLPM. LPM stands for Linear Program Master. We've seen how we can write the linear program master problem in vector notation. When we focus on a subset of columns, we're going to introduce a new quantity, z tilde linear program master. Z tilde is the solution associated with looking at just a subset of columns. To denote that we're looking at a subset of columns, we change all of our vector notation to tildes. We look at the vector c tilde times lambda tilde, the matrix A tilde times lambda tilde, the matrix E tilde times lambda tilde, and the vector lambda tilde. Each of these tildes are associated with a particular subset of columns, but the columns need to be generated in a particular way. The easiest way to see how these columns are generated is to look at our matrix A and see how we're going to generate our new matrix A tilde from A. First, we write the matrix A. The matrix A consists of k separate matrices. These separate matrices are A1 through AK. Each one of these matrices is our original matrix A multiplied by the feasible solutions in the corresponding set. For example, A1 is our original matrix A multiplied by all the feasible solutions associated with set S1. Alternatively, the feasible solutions inside of the set capital X1. If we expand out each one of these A's, we're going to see a large collection of columns. We're going to focus on A1. A1 contains capital T1 columns. Remember, capital T1 is the number of feasible solutions in capital X1. There's one column associated with each feasible point inside of capital X1, and so we have capital TI columns. The same is true for all the other A's. A2 has capital T2 constraints, or rather T2 columns, and capital AK has capital TK columns. We should note that capital A, our original matrix, has a huge number of columns. We're going to restrict this number of columns by producing A tilde. A tilde is produced by selecting a subset of columns from each one of the AIs. For example, looking at A1, we select a few of the columns from A1. There has to be at least one column from A1 chosen. In this case, we've chosen the first column, A1, 1, and also some other columns in the middle. For formula A2, we do the same thing. We have to select at least one column, and we can select as many as we'd like. In this case, we select two columns somewhere in the middle. We do the same thing for all of the indices 1 through k. This formulates a new set of matrices, A1 tilde, A2 tilde, through AK tilde. Each one of these AI tilde matrices includes some subset of columns from the original AI. A tilde, then, is the matrix formed by composing all of these matrices with one another. We can see exactly how we've chosen columns. We've expanded our matrix A so that we see all of the columns, each column associated with each feasible solution in each of the capital Xi's. Then, in each of the Xi's, we choose some subset of feasible solutions and place those columns in our new matrix A tilde. We do the same thing for all the other tildes. C tilde is formulated by choosing the same columns that we've chosen in A, and E tilde is formulated by again choosing the same columns that we've chosen in A tilde. By doing this, we have a restricted linear program. The columns are the columns associated with this A tilde matrix. This program, then, Z tilde LPM, is a new program, linear program, that's much smaller than our original one. It's smaller because we've only chosen a subset of the columns. One simple and useful fact is that when we choose a subset of columns, our solution value is going to be a feasible solution to our original problem. We formulate this, or rather describe this, by saying that if we look at our original master program, ZLPM, the solution value of this program has to be at least as large as the solution value of Z tilde. This is because Z tilde is a restriction. We've only included a subset of columns, And so we can only look over a subset of the feasible solutions. The feasible solutions we're looking over correspond to the feasible solutions associated with the columns that we've introduced. Once we solve z tilde LPM, we get some solution, lambda tilde, and this solution, lambda tilde, can be plugged in and immediately be a feasible solution to our original master problem.